So today we're going to be solving October-November 2021, paper 11. Here we have question number 1. Question number 1 says the mass spectrum of a sample of neon is shown. The relative abundance of each peak is written in the brackets above it. What is the relative atomic mass of this sample of neon? Now over here what we have is, to calculate the relative atomic mass, remember the relative atomic mass is the weighted average mass of these isotopes, right? Now what we have is, first of all, what is the sum of the abundances of each of the isotopes? It's not 100 over here. It will be 100 plus 0.3 plus 8. So what we have is 108.3. That's the sum of the abundances. So we have a total of 108.3 atoms. That's how you can think about it. Out of this total of 108.3 atoms, 100 of them have a mass of 20. Okay, 0.3 of them have a mass of 21, and 8 of them have a mass of 22. So if I had a total of 108.3 atoms, 100 of them have a mass of 20, 0.3 have a mass of 21, and 8 have a mass of 22. So this is their total mass, right, for these isotopes, and their average mass will be divided by the total number of atoms. So what does the relative atomic mass come out to? This comes out to 20.15. So the answer over here is A. 2 grams of ammonium nitrate decomposed gives 0.9 grams of water and a single gas. What is the identity of the gas? So what we have over here is we have ammonium nitrate decomposing to give us some gas. Okay, it's giving us some gas and H2O, right? Now you look at the possible answers, right? None of the gases have hydrogen in them. So that means all the hydrogens have gone with the water. All the hydrogens have gone with the water. So how many H2Os do we have for every one of ammonium nitrate? If I have one ammonium nitrate, right, that's 4 hydrogen atoms. So I'm going to need 2 H2O, right? So then how many nitrogens am I left with? I have 2 nitrogens left and 1 oxygen. So that leaves us with N2O. So the answer over here is C. Over here, you don't have to use the masses at all. We know that we're getting 0.9 grams of water and some gas, okay? So what that means is that if you look at the possibilities, all the hydrogen atoms go with the water. So if I had 1 mole of ammonium nitrate, right, I have 4 hydrogen atoms here. So that means I have 2 H2O. Now if I have 2 H2O, so I have 2 oxygens on the right, but I have 3 oxygens on the left. I have 2 oxygens on the right, but 3 oxygens on the left. That leaves us with 1 oxygen atom. And I have 2 nitrogens on the left, so I'm going to have 2 nitrogens on the right. So we get this molecule must have 2 nitrogen atoms and 1 oxygen atom, just to balance it out. Here you could also find the moles of ammonium nitrate and the moles of water, and you'd realize that for every 1 mole of ammonium nitrate, you have 2 moles of water. The moles of ammonium nitrate to water will give you a 1:2 ratio. Okay, so you can calculate the moles and then find the moles of water for every 1 mole of ammonium nitrate. Okay, you can use the molar ratio from calculation to determine this equation as well. But in this particular case, you don't have to, because given the answers, we know all the hydrogen atoms are going with the water. Okay, so we can deduce the molecular formula of the gas. Question number 3 says, which of these elements has the highest fifth ionization energy? Now, generally speaking, which elements will have a very high fifth ionization energy? Or in other words, for which group will we have a large jump between the fourth and the fifth? For which group will we have a large jump from the fourth to the fifth? The fifth ionization is very high. That means there are 4 outer electrons. So that means group 14, right? And what do we have in group 14 over here? It's either carbon or silicon, right? We have carbon and silicon. These are in group 14. And which one of these do you think has a higher fifth ionization energy? Would it be carbon or silicon? If you go down the group, the ionization energy decreases. So that means carbon would have the highest fifth ionization energy. For nitrogen and phosphorus, there's 5 outer electrons. So the fifth ionization energy wouldn't be as high as for silicon and carbon, because for carbon and silicon, after you remove the 4 outer electrons, the fifth one will be removed from an inner shell. And because carbon is higher up in the group, right? So silicon has more shells, it has a lower fifth ionization energy, whereas carbon will have the highest. The ion X2 plus has the same electronic configuration as the atom krypton. What is the electronic configuration of an atom of X? So when we look at the periodic table, we see that krypton, right, is in period 4 and it's a noble gas, right? So the electronic configuration for krypton will be 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, right? Noble gases end with p6, right? And we know that's in the 4th period, so it ends with 4p6. And X2 plus has the same configuration as krypton. X2 plus has the same configuration as krypton. So then what is the configuration of X? What is the configuration of X? X2 plus has 2 fewer electrons. It has 2 fewer electrons. So the answer here would be B. Okay, they've written it as 4s2 3d10 rather than 3d10 4s2. That's fine. Okay, in our syllabus we usually write 3d10 4s2, but this is also acceptable. Okay, this is how, for example, American textbooks would write it. Okay, so you can say 3d10 4s2, or you can say 4s2 3d10 4p6, and then that's for the 2 plus ion. So the atom itself will add 2 additional electrons, so that will be 5s2, right? So those are the 2 additional electrons for the atom over here. So the answer here is B. Question number 5. Which type of interaction exists between water molecules and metal cations in aqueous solution? So water is a polar molecule, right? Water is a polar molecule. So we know that it has a net dipole, right? It has a net dipole. It doesn't show ionic bonding. It has a net dipole. So if water with itself hydrogen bonds, but with a metal cation, right? Metal cations have ions, right? So that means that these ions will form an attraction with this polar molecule. So what you have is a permanent dipole and an ionic attraction, right? You have a permanent dipole being attracted to a positive ion. So what we have is ion dipole attractions. Okay, so the answer here is C. It's not dipole because metals have their ions, right? These cations are ions, so it's not dipole. Metals don't have hydrogen bonding, right? And we know that obviously water doesn't show ionic bonding. Which substance shows the greatest deviation from the properties of an ideal gas under room conditions? The greatest deviation. In other words, it behaves least like an ideal gas. Now, for the ideal gas, we assumed that ideal gas, right, they occupy the molecules. The 2 main assumptions that you have to remember are that the molecules occupy negligible space, okay? They occupy negligible space. The molecules themselves. So the gas occupies a large volume, but the molecules themselves have 0 volume, okay? And we also assume that there are no intermolecular forces. So in which of these cases are these assumptions least true? So where do you have the strongest intermolecular forces here, for example? Right? We know that ammonia has hydrogen bonding. All the other ones are temporary dipoles, right? So the stronger the intermolecular forces, the less ideal the gas. The weaker the intermolecular forces, the closer they are to this assumption, no intermolecular forces, right? That's an assumption. Jitni zyada intermolecular forces, the stronger the intermolecular forces, the less ideally a gas behaves. So the answer here is D, because ammonia has hydrogen bonding. That's the strongest intermolecular force, so it's furthest from this assumption. In order to determine the enthalpy of neutralization of a strong acid and a strong alkali, 25 cm cube of 2 mole per dm cube sodium hydroxide is added to 25 cm cube of 2 mole per dm cube hydrochloric acid. The increase in temperature is 12 degrees Celsius. In a second experiment, the same method is used, but you have 50 cm cube of 2 mole per dm cube sodium hydroxide and 50 cm cube of 2 mole per dm cube hydrochloric acid. What is the increase in temperature in the second experiment? When we talk about the increase in temperature, right, we know that if we, for calorimetry, we have Q is equal to MC delta T, right? That means that delta T is equal to Q over MC, right? Here M is the mass of water. Now we know that the heat released will be double. We're going to release double the amount of heat because we have double the amount of acid and double the amount of alkali, right? We're going to make twice the amount of water. We have the same concentrations, right? But here we have 25 cm cube of 2 mole per dm cube and 25 cm cube of 2 mole per dm cube. So our final solution is 50 cm cube. Our final solution here is 50 cm cube in the first experiment, right? So the mass of water is 50 grams. Now when we double the amount of acid and alkali, what we're doing is we're releasing twice the amount of heat. But we also have twice the amount of water. Now we have 100 grams of water. Now we have 100 grams of water. That means the mass has been doubled, but so has the heat being released. We have double the amount of acid and alkali. We have twice the amount of water being produced in the neutralization, twice the amount of heat being released, but we also have twice the mass of water. So ultimately, the change in temperature is the same, right? So the answer, therefore, is B. All right, question number 8. Which equation represents the enthalpy change of atomization of iodine? Now, atomization is no longer part of your syllabus, but atomization is basically the formation of 1 mole of gaseous atoms from the elements in their standard state. Okay, so the answer here is C. 1 mole of gaseous atoms from the elements in their standard states. Okay, so the answer here is C. But again, as I said, atomization is no longer part of the AS syllabus. Okay. Zinc atoms can be oxidized to Zn2 plus by dichromate 6 ions in acid solution. Chromium is reduced to Cr3 plus in this reaction. Which equation is correct? So here we need to determine which is the correct balanced equation for this reaction. Okay, and the way to do this is the following, right? We know that zinc is being oxidized. We know zinc is being oxidized, okay, from 0 to +2, right? Whereas chromium is being reduced from +6, right, in dichromate 6, right? Chromium is +6 and it's being reduced to +3, right? So that means that what's the change in oxidation number for zinc? What's the change in oxidation number for zinc? The change in oxidation number over here is +2, right? The change in oxidation number here is +2. And the change in oxidation number for chromium is -3. Now we know that for any redox reaction, the increase in oxidation number has to balance the decrease. So can I say that for every 3 zinc atoms, I'm going to have 2 chromium atoms undergoing reduction. For every 3 zinc atoms undergoing oxidation by +2, I'll have 2 chromium atoms being reduced by -3. So that means the ratio of zinc to chromium is 3:2. So that means I have 3 zinc atoms for every 2 chromium atoms, right? And obviously on the left also I'm going to have 2 chromium atoms and 3 zinc atoms. So the answer is C. Okay, on the right also I'll have 3 zincs and 2 chromiums, and on the left also obviously the zinc and the chromiums have to be balanced. For options B and D, right, over here the balancing is correct, but on the left hand side the zinc isn't balanced. Similarly for option D, right, we can see that on the right they're balanced, but on the left the chromium isn't balanced. So the only possible answer here is C. So here we have question number 10. The equation shows that hydrogen and iodine react to form an equilibrium mixture. A mixture containing equal amounts of hydrogen and iodine is made at temperature T1 and the composition of the mixture is monitored. A graph of the results is shown. And they've shown the mole fraction of iodine. That is the moles of iodine divided by the total number of moles of all the substances. Okay, and they're obviously the mole fraction is decreasing over time since we're starting with hydrogen and iodine, and eventually we're going to reach equilibrium and we'll have lesser iodine than we started with, right? The experiment is repeated at a lower temperature T2. Which new graph would be obtained? So what we have is we're repeating the experiment at a lower temperature. We're repeating it at a lower temperature. So now the question is, when we talk about the lower temperature, right, we want to talk about the rate and we want to talk about the yield, right? What happens to the rate of the reaction at a lower temperature? Like, does iodine decrease faster or does it decrease slower at a lower temperature? The rate will obviously decrease, right? Because we have a lower temperature, lower average kinetic energy. So that means the iodine will decrease slower, right? It'll be a shallower increase, right? It'll be a shallower increase like this, right? Now the second question I have is, if I have a lower temperature, over here, right, we have an exothermic reaction. You know, a decrease in temperature favors the yield of the reaction, right? Because it's an exothermic reaction, a decrease in temperature favors the exothermic side. So the yield of the product, hydrogen iodide, will increase. We'll have more of this, and lesser of iodine. So the mole fraction of iodine should be even lesser at equilibrium because the equilibrium shifts to the exothermic side. Lower temperature, the exothermic reaction is favored, higher yield of products, lesser amount of reactants, so lesser amount of iodine. So the graph will look something like this, right? So then the answer over here would be what then? It would be B. Next we have question number 11. It says the diagram shows the Boltzmann distribution of energies for a reactant gas. For a particular reaction, the activation energy is X. Which change to the diagram occurs if an effective catalyst is added at the same temperature? So at the same temperature, remember a catalyst, what it does is it decreases the activation energy. It decreases the activation energy, right? So we'll have a lower activation energy. We have the same temperature, so the curve isn't affected. We have the same curve, so the peak doesn't move at all, right? And the energy of the particles is therefore also not affected. Okay, the energy of the particles remains the same. We have the same curve, right? We have the same curve, so the peak remains the same, but the value of the activation energy decreases. Okay. Which element requires the least number of moles of oxygen for the complete combustion of 1 mole of its atoms? So here the answer is simply D, right? I mean, we can verify this. Aluminum, right, forms Al2O3. So if you have 1 mole of aluminum, you're going to need 3/2 moles of oxygen. Okay. Magnesium, for 1 mole of magnesium, you need half a mole of oxygen, right, to form MgO. For phosphorus, right, P4, you're going to need 5 oxygens, okay, to get P4O10. And for sodium, right, if you have 1 mole of sodium, you're making Na2O. So that's half Na2O. So you're going to need a 1/4 mole of oxygen gas. So you're going to need the fewest number of moles of oxygen for sodium. So the answer here is D, right? Since you have 1 mole of sodium, you're going to have half Na2O, right? 1 sodium. So that means 1/4 oxygen, or 1/4. An element Y reacts according to the following sequence. It burns an oxygen to form a white solid, which reacts with HCl to give us a solution. With NaOH aqueous, it gives you a white precipitate, and with an excess of NaOH aqueous, it gives you a solution again. What could be element Y? The answer over here is aluminum, right? And the reason why is this. So when aluminum burns an oxygen, right, you form Al2O3. And we know that Al2O3 is amphoteric. It reacts with an acid to form a solution, right? Reacts with acid to form a solution. And we know that if we add sodium hydroxide aqueous, right, what we get is we get aluminum hydroxide. We get aluminum hydroxide. But if you have an excess of sodium hydroxide aqueous, you end up making this anion, right? If you guys remember, excess sodium hydroxide dissolves aluminum hydroxide, right? So you end up making this salt, okay? This salt is Na plus and AlOH4 minus. So if you add NaOH aqueous drop by drop, you make aluminum hydroxide, which is a white precipitate. With an excess of NaOH, you make this guy, which is soluble in solution. So the answer here is C. In which list are all 3 compounds soluble in water? The first thing you should know is that group 2 carbonates are insoluble in water. So we know that calcium carbonate and strontium carbonate are out. We also know magnesium hydroxide is insoluble. So barium chloride is soluble, barium hydroxide is soluble, calcium hydroxide partially, very partially soluble. Okay, it can be considered to be insoluble. What about this guy here? Barium chloride, yes. Barium hydroxide, yes, because hydroxide solubility increases down the group. So barium hydroxide is soluble, so is strontium. Okay, and magnesium sulfate, yes. For sulfates, the solubility decreases down the group. So barium, even calcium sulfate is partially soluble. Barium sulfate is insoluble. Same with strontium. But magnesium sulfate is soluble. So the answer is C. Okay. Anhydrous magnesium nitrate decomposes when heated, giving a white solid and a mixture of 2 gases, X and Y. Y is oxygen. What is the ratio mass of X released divided by the mass of Y released? Now, if you guys remember, for group 2 nitrates, right, when we decompose them, we form the oxide. For every 1 mole of group 2 nitrates, you're going to form 2 moles of nitrogen dioxide and half a mole of oxygen gas, right? So can I say over here that X over here is obviously nitrogen dioxide. So the mass of X released will be the mass of X released, which is the mass of nitrogen dioxide, is equal to the number of moles times the molar mass. So we have 2 moles, and the molar mass over here is nitrogen is 14, right? Nitrogen is 14, and then oxygen is We have 2 times 16, so that's 32 plus 14, so that's 46. So this is 92 grams. Okay, so for 2 moles of nitrogen dioxide have a mass of 92 grams, whereas half a mole of oxygen, that's Y, right? Half a mole of oxygen has a mass of half times 32, right, which is 16 grams. So that means the ratio over here, we want the ratio mass of X divided by mass of Y. That is 92 divided by 16, right? So what's 92 divided by 16? Now over here, if you notice, in all the answers, 1 is in the numerator. So what's 16 over 92? Can someone tell me what's 16 over 92? 16 over 92 comes out as 0.174. So then what's 92 over 16? 92 over 16 would be 1 over 0.174. Okay, the reason I did 16 over 92 first is because when you do division, right, when you do division, you normally get 1 in the denominator, right? But here, since we want to reverse it, right, we just do 16 over 92, we get 0.174, and then if we flip it, we get 1 over 0.174. So that means that this is equal to 1 over 0.174. So the answer here is A. Here we have question number 16, which says, in a series of 9 experiments to test the reactivity of the halogens, an aqueous solution of each halogen is added to an equal volume of an aqueous solution containing halide ions, as shown in the table. The 9 resulting mixtures are then shaken separately with an equal volume of hexane. The 9 tubes are left to stand so that the aqueous and organic solvents separate into layers. How many test tubes contain a purple upper hexane layer? So that means in how many solutions do we have iodine? Okay, and how many solutions do we have iodine? Right, that's what the question is asking. So when we talk about chlorine, right, we know chlorine is the strongest of the oxidizing agents and iodide is the strongest of the reducing agents. So chlorine can oxidize bromide and iodide, right? Obviously there's no iodine here, but we know that we're going to get iodine over here because chlorine will be able to oxidize iodide to form iodine. Now, what about bromine? Would bromine be able to we don't care about bromine and chloride, right? We don't care about bromine and bromide either, right? Will bromine be able to oxidize iodide? Would bromine be able to oxidize iodide? Again, yes, because bromine is a stronger oxidizing agent, right, than iodine. So bromine will be able to oxidize iodide. So we're going to get iodine again, right? Now, in this particular case, would iodine be able to oxidize chloride? Would iodine be able to oxidize chloride over here? It won't. So will we still have iodine over here? Would we still have iodine left over? Since iodine is not reacting at all, would we have iodine left over in this experiment? Yes. So because this reaction doesn't happen, we're going to have iodine. Same thing here, iodine cannot oxidize bromide. So again, you're going to have iodine. And obviously with iodine and iodide, you're also going to have iodine. So then in how many of the experiments do we have iodine? In 2 of the experiments, iodine is produced. And in 3 of the experiments, iodine remains in solution. So the total amount is 5 different experiments we're going to have iodine. Question number 17. Z is a compound of sodium, chlorine, and oxygen. It contains 45.1% biomass of oxygen. Z is prepared by reacting sodium hydroxide with chlorine. Which row shows the conditions used for the reaction and the oxidation state of chlorine and Z? Now, first of all, we know that with cold dilute NaOH, right, we get NaClO. With cold dilute NaOH, right, we get NaClO. And with hot concentrated NaOH, right, we get NaClO3 as the chlorine, sodium, and oxygen products. Okay, these aren't obviously the overall equations, but these are the compounds we're interested in. In sodium chlorate 1, chlorine has an oxidation state of +1. In sodium chlorate 5, chlorine has an oxidation state of +5. So first of all, we know that with cold dilute, we don't get the +5. So we can eliminate B. And with hot concentrated, we don't get the +1. So we can eliminate C as well. Okay, so this already increases our chances to 50%. Okay, even if you didn't know how to solve for this. But now let's solve for it. Which of these has 45.1% biomass of oxygen. 45.1%. So here oxygen has a mass of 16 divided by 35.5 plus 23 plus 16, right? That's the total MR of this molecule. This doesn't seem like 45.1%. If you multiply this by 100, what percentage do you get here? This is 21%. So we know that it's not NaClO. So it must be NaClO3. Okay, so the answer is D. You can verify this, right? We have 48 as the 3 oxygen atoms over here. Then we have 23 plus 35.5 plus 48, right? And multiply this by 100. What does this come out to? And this comes out to 45.1%. Okay. Although we don't really need to do this calculation here. You can just do one of the calculations, right? You can either calculate this or this, right? The other one will obviously, you can deduce that which is the answer. Which row is correct? What's the shape of an ammonia molecule and an ammonium ion? And the bonds present in an ammonia molecule and an ammonium ion. So what's the shape of an ammonia molecule? Is it pyramidal or tetrahedral? When we talk about ammonia, ammonia has a pyramidal shape. And if you talk about ammonium, what's the shape of an ammonium ion? Ammonium has a tetrahedral shape, right? It's a regular tetrahedron, right? This is the ammonium ion. So we know that ammonia is pyramidal and ammonium is tetrahedral, right? And what are the bonds present? Do either of them have pi bonds? Do you see any double bonds here? Do you see any pi bonds on either of them? No, right? They both have sigma bonds. So the answer here is A. Okay. The table describes 2 possible environmental consequences of adding too much ammonium nitrate fertilizer to the soil. Which row is correct? This is no longer part of your syllabus, okay, as far as fertilizers are concerned, but we know that nitrate fertilizers, when they wash into the water, right, when the nitrates wash into the water, right, we have algae growth. So there is increased plant growth in rivers, okay, in bodies of water. Whereas photochemical smog is not a result of nitrates. Photochemical smog is a result of oxides of nitrogen that you get from combustion engines, right, or from lightning. That's the natural cause for it. But generally speaking, right, it's from car engines as far as pollution is concerned. So the answer here is B. Okay. Hex-2-ene can be made by the reaction shown. Which statement about this reaction is correct? CH3 thrice CO minus is behaving as a Bronsted-Lowry base. Well, it's accepting a proton, so therefore it is a Bronsted-Lowry base. So the answer here is A. Okay. Again, by definition, a Bronsted-Lowry base is a species that accepts a proton. So isn't this guy, ultimately, you had this guy, right, O minus, and when this combines with H plus, you end up producing this, right? Because the electrons from this bond are going back into the structure, right? So this guy is actually accepting a proton. This guy is accepting a proton, hence it's a Bronsted-Lowry base. By definition, a Bronsted-Lowry base is a proton acceptor. Okay, it's not behaving as an oxidizing agent. Okay, the Ci bond is breaking via heterolytic fission, not homolytic fission. This is not a hydrolysis reaction either. Okay. Structural isomerism only should be considered when answering this question. Molecule X contains 3 carbon-carbon double bonds. 1 mole of X is reacted with 3 moles of HBr. The carbon skeleton is unchanged. How many different products are formed? Now, first of all, if you look at this molecule, is this a symmetric molecule or not? We're adding HBr, right? This is addition of HBr. 1 mole of X is reacting with 3 moles of HBr. So that means HBr is being added to each of the double bonds, right? HBr is being added. But the question is this a symmetric molecule? First of all, we can clearly see this is a symmetric molecule, right? We can clearly see that this is a symmetric molecule. If you draw a line of symmetry over here, you see this right-hand side is identical to the left-hand side, right? So we have a symmetric molecule over here. Now, so if you look at the middle double bond, does it matter where I add the HBr, if I add it here or here, right? I can add it here or there, it doesn't matter, right? Because ultimately you can just flip it around, you'll get the same molecule. Agreed? If I add the H here or the Br here, it's the same thing. because left and right are identical. What I mean by that is, if, for example, instead of having the H on the left and the Br on the right, right? If I had it like this, Br on the left and H on the right, it's still the same thing, right? It doesn't matter if I put the H here or the Br there, right? It's the same thing. Because it's symmetric, right? It doesn't matter where I add the H and the Br. Now the question is on the ring. On the ring, now what we have is we have two identical rings over here, right? But now we've added HBr. Now what this means is, if you look on the side of the bromine, right? Now what you're going to do is you're going to add an HBr and an HBr here, right? And an HBr over here. You're going to add it in two different places. Now you could add a bromine atom closer to this. You could add a bromine atom over here, right? And an H over here. Same thing here. You could add a bromine atom on position let's call this position 1. So you could add a bromine atom on position 3, right, on the ring in both cases, and a hydrogen on position 4, right? That's one possibility. Bromine is closer to this carbon chain and hydrogen is further away from this carbon chain, right? That's one possibility. What's the other possibility? The other possibility that we have is that the bromine is further away and the hydrogen is also further away. Bromine is further away, and on the other side also the bromine is further away, whereas hydrogen is closer, right? They're not the same anymore. Well, first what we did was we put the bromine on position 3, now we put the hydrogen on position 3, right? So one possibility is both the bromines are closer to the carbon chain, the other possibility is both the hydrogens are closer to the carbon chain. A third possibility that we have is on the side of the bromine, okay, on the side of the bromine, okay, we can say that the bromine is closer and the hydrogen is further away, okay, and on the side of the hydrogen, we can say that the hydrogen is closer and the bromine is further away, right? Again, you're looking at it relative to the carbon chain, okay? So in this case, on the side with the bromine is closer to this carbon chain and hydrogen is further away, and on the side with the hydrogen, the bromine is closer and the hydrogen is further away. The last possibility that we have is that on the side with the bromine, the hydrogen is closer instead of the bromine now. Okay, the hydrogen is closer and the bromine is further away. And on the side with the hydrogen, the bromine is closer and the hydrogen is further away. Okay, so we have a total of 4 possibilities. The reason why this was different from the previous case was because we no longer have a line of symmetry. Once we add HBr, we don't have a symmetric molecule, right? So therefore, you know, it does matter. In this particular case, this bromine is closer to this hydrogen, but the bromine here is further away from the bromine relative to this hydrogen. Whereas in the other case, the Br was here and the H was here, and the Br was here and the H was here. So we just switched the HBr, okay, in both of these. So the answer that we have over here is B. Okay, there are 4 different possibilities. Question number 22. Structural isomerism and stereoisomerism should be considered when answering this question. A colorless liquid, C5H11Cl, exists as a mixture of 2 optical isomers. When heated with sodium hydroxide and ethanol, a mixture of only 2 alkenes is formed. What could the colorless liquid be? So first of all, if it exists as a mixture of 2 optical isomers, it has what type of a carbon? It has a chiral carbon, right? Or a chiral center. Okay, it has a chiral center. So one of the carbon atoms is bonded to 4 different atoms or groups of atoms. The second idea is that when we eliminate HCl from this molecule, when we remove HCl, we get only 2 alkenes being formed. Now, if you look at the possibilities, does A have a chiral center? Does it meet the first condition here? This carbon is bonded to 2 identical ethyl groups. So this doesn't have a chiral center, so we can eliminate A. What about B? Does B have a chiral center? It has an H, a Cl, a CH3, and a CH3, CH2, CH2. So here we clearly see that we have a chiral center. Okay. What about this case here? Do we have a chiral center here? This carbon is bonded to two identical methyl groups. This carbon is bonded to two identical methyl groups. So again, this is not a chiral center, so we can eliminate C, right? And then we have D. In D, we have a chiral center again, right? This is our chiral center. This carbon is bonded to a hydrogen, a chlorine, a CH3, and this CH3 twice CH group, this entire group over here. So it's bonded to 4 different atoms or groups. So now we're only left with B or D as our possibilities. Now if you look at option B, this is what we have in option B, right? We have 2-chloropentane. Okay. Now if we eliminate, we have an elimination reaction taking place. Right? One possibility that we have is we remove the chlorine and the hydrogen from the neighboring carbon. Okay, so we can remove this chlorine and this hydrogen. That leaves us with pent 1-ene, right? That's one alkene that we're forming. The other possibility that we have over here is that instead of removing this hydrogen over here, we're going to remove this hydrogen in the middle. If we remove the hydrogen in the middle, then what do we get? Then we get pent 2-ene. Right? So we get this guy, CH3, CH2, CH, double bond CH, CH3. But now pent 2-ene, is this structural formula, does it represent one alkene or two alkenes? This particular structural formula, does it represent one alkene or two alkenes? In other words, does this show stereoisomerism? Yes, right? This is cis-trans isomerism. We know that we can have either trans pent 2-ene, right? That's 1, 2, 3, 4, 5, trans pent 2-ene, or we can have 1, 2, 3, 4, 5, or we can have cis pent 2-ene. We can have trans or cis pent 2-ene. So this structural formula is actually for two different alkenes, either cis pent 2-ene or trans pent 2-ene. So that how many alkenes do we get in total? We get pent 1-ene, we can get cis pent 2-ene, or we can get trans pent 2-ene. So there's a total of 3. So are only 2 alkenes being formed here? No, we're forming 3 alkenes over here. So the answer over here is D. Question number 23. When 2-bromo-2-methylpropane reacts with aqueous sodium hydroxide and alcohol is formed, which diagram describes the first step in the reaction mechanism? Now over here you have 2-bromo-2-methylpropane. Okay, so you have a 3-carbon chain, right? That's propane. And then you have a CH3 and a bromine, right? So you have a tertiary halogenoalkane here. For a tertiary halogenoalkane, you're going to have the SN1 mechanism. That's a 2-step mechanism. So in the first step, you just have heterolytic fission. Okay? And in the second step, right? After the first step, you form a carbocation intermediate, right? And then in the second step, you end up bonding the hydroxide to the hydroxide attacks the carbocation to form the final product. Okay, so in the first step, what do we have? We just have hydrolysis taking place. So which part over here shows the correct first step? We know that the hydroxide isn't involved until the second step. Hydroxide bonds with the carbocation intermediate in the second step. Okay, so it's not involved until the second step. That means in the first step we just have hydrolytic fission, so that leaves out C and D, right? And then we know that we have a delta positive carbon and a delta negative bromine over here. So the answer here is B. Okay, it's not, A is incorrect. The electrons go to the bromine. Okay, so this arrow is shown correctly here. When an organic compound Q is treated with phosphorus pentachloride, that's PCl5, fumes of hydrogen chloride are evolved. When Q is warmed with acidified aqueous potassium dichromate 6, the solution turns green. What is Q? So it reacts with PCl5. Right? And if you guys remember, and we're producing HCl. What is PCl5 a test for? Does anyone remember? PCl5 is a test for the OH group. It's a test for the OH group. Okay, so we know we have an OH group. So that could be, obviously, it could be the acid, it could be any of these two alcohols. But they're also saying that with acidified dichromate, the solution turns green, from orange to green, right? With potassium dichromate, we go from orange to green. So that means this species undergoes oxidation. So we have an OH group, and we have oxidation taking place. Now the carboxylic has an OH group, but will it undergo oxidation? Will it undergo oxidation with dichromate, carboxylic acid? No, right? Now we have two alcohols here. Here we have a tertiary alcohol. Here we have a secondary alcohol. Which one will undergo oxidation? We know tertiary alcohols can't be oxidized. We know tertiary alcohols don't undergo oxidation. So this won't react with dichromate either. Only the secondary alcohol can be oxidized. So the answer here is C. Alcohol Y gives a yellow precipitate with alkaline aqueous iodine. It can be oxidized to give a mixture of products, including substance Z. Substance Z gives a red-brown precipitate with Fehling solution. Which alcohol could be Y? Now this reaction, right, the yellow precipitate with alkaline aqueous iodine is known as the iodoform reaction. And since we have an alcohol, it means that this alcohol must contain this group. Okay, this group is necessary for the iodoform reaction. This group is necessary for the iodoform reaction. Okay, and the alcohol also gives, when it's oxidized, when the alcohol is oxidized, it gives a substance that gives a red-brown precipitate with Fehlings. That means when we oxidize the alcohol, we can get a CHO group. When we oxidize the alcohol, we can get a CHO group. So that means that it must be there's also a primary alcohol group over here. So we have this alcohol group present. Okay, this is for iodoform. We have this alcohol group present for the iodoform reaction, and we have this alcohol group present for we have a primary alcohol present because we're getting oxidation is giving us a CHO group, right? Which we also find in aldehydes. Okay, so it has to be a primary alcohol. So which alcohol has both of these groups? Which alcohol has a CH3CHOH and a CH2OH? The answer over here is A. We have the CH3CHOH group, right? This will undergo the iodoform reaction to give you that yellow precipitate of triiodomethane, and it has a primary alcohol group. Okay, so the answer here is A. CH3CH2CO, CH2CH3, that's pentane 3-one, reacts with hydrogen cyanide to form an organic product called a cyanohydrin. Which statement is correct? So what we have over here is we have this ketone, right? We have this ketone over here. And when this reacts with HCN, this is the product that we end up making, right? This is nucleophilic addition of HCN. This is nucleophilic addition of HCN. Now my question here is this. Which statement is true about this reaction? Does the product have a chiral center? No, because this carbon is bonded to two identical ethyl groups. So statement A is incorrect. It's not electrophilic addition. The intermediate does not contain a COH group. Okay, in the first step of this reaction, what happens is that the CN minus attacks the carbon. Okay, and the intermediate looks like this. Right? This is what the intermediate looks like. So it doesn't have an OH group. So that's incorrect. The formation of the cyanohydrin product requires the use of cyanide ions as a catalyst. This is true. If you guys remember, for addition of HCN, you need HCN aqueous, okay, in NaCN aqueous. You can use NaCN or KCN aqueous. Here, sodium cyanide or potassium cyanide act as the catalyst. So we're going to need cyanide ions as catalysts, okay, because these salts ionize completely, so we have more cyanide ions for this reaction. Okay, so the answer is D. Okay. Reduction of compound R with LiAlH4 gives the compound 4-methyl pentane 2,3-diol. What could be the identity of compound R? So what we have over here is we have our final product, okay, is 4-methyl pentane 2,3-diol. So that's 1, 2, 3, 4, 5, right? We have 2,3-diol, so OH and OH, right? And we have a methyl group on carbon number 4. Now, which of these compounds can be reduced to give us this? Just look at the positions of the OH groups, right? We can see that in A, we have a ketone on carbons 2 and 3. That will give us the alcohols on carbons 2 and 3. And we have a methyl on carbon number 4. So the answer here is A. Okay. When this guy is reduced with LiAlH4, right, in dry ether, anhydrous LiAlH4, we'll get this as the product. Okay. Citric acid is found in lemon juice. Which volume of 0.4 mole per dm cube sodium hydroxide solution is required to neutralize a solution containing 0.005 moles of citric acid? So the first question I have is, right, they've given us the moles of citric acid. So if I have 1 mole of citric acid, how many moles of NaOH would I need? How many moles of NaOH would I need? I would need 3 moles of NaOH. I would need 3 moles of NaOH needed for neutralization. Why? Because one citric acid molecule has 3 CO2H groups. For every 1 CO2H group, I need 1 NaOH molecule, right? Right? This is what the neutralization would look like. That is, for every 1 CO2H, for 1 mole of CO2H, I need 1 NaOH, 1 mole of NaOH. If 1 mole of citric acid has 3 moles of CO2H, right, it has 3 moles of CO2H, I'm going to need 3 moles of sodium hydroxide. So then, if I have 0.005 moles of citric acid, how many moles of NaOH would I need? How many moles of NaOH would I need? I would need 3 times as much. So then I would need 0.015, right? I would need 0.015 moles of NaOH. So therefore, we figured out the number of moles of NaOH needed. We need 0.015 moles. So then can we figure out the volume, right? We have the concentration and we have the number of moles. We know number of moles is concentration times volume. The number of moles is 0.015. The concentration is 0.4. And the volume is what we have to find. So the volume would be 0.015 divided by 0.4. So what does that come out to? So here you should get 0.0375 decimeter cube. 0.0375 decimeter cube, right? That's in centimeter cube. If you just multiply this by 1,000, you get 37.5 centimeter cube. So the answer over here is C. Okay. The structural formula of an ester is given here. The ester is boiled with aqueous hydrochloric acid. Which 2 products are formed? Okay. So let's draw out the ester over here. We have this carbon is bonded to 2 CH3s. So we have C, 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 right? And then we have OCO. Now, if you see this OCO over here, right, that means that on the left, they've given us the alcohol part of the ester. Okay. So the OCO means you have an O, a C, double bond O, and then you have CH2, CH2, CH3. Okay. CH2 twice and then CH3. So this is our ester over here. Okay. This is our ester over here. And if we're going to hydrolyze this, with hydrochloric acid, this is acidic hydrolysis, right? We're going to break the ester linkage. So we're going to get an H over here and an OH over here. So what acid are we getting? This acid. This is a 4-carbon acid. So this is butanoic acid. This is butanoic acid, right? So we know for a fact that we're getting butanoic acid. And then what alcohol are we getting? We have an OH on the middle carbon. I haven't shown the hydrogens here, obviously. So this is propan 2-ol, right? This is propan 2-ol. We have a 3-carbon alcohol and a 4-carbon acid, but the OH group is on carbon number 2, right? So this is propan 2-ol and butanoic acid. This over here is your alcohol chain, right? So if you when you have an H coming on this oxygen here, right, this is the ester linkage that's breaking. So this is the OH group from the alcohol, right, will become the OH group. So then on carbon number 2 we'll have the OH group. Okay, just again guys, a reminder, this is still propan 2-ol. This is still a 3-carbon. If you draw it like this, it's still a 3-carbon chain. Okay, still a 3-carbon chain with an OH on carbon number 2. Just because I've drawn it crooked like this doesn't mean that it's branched. Okay, I can still trace out the carbon chain in one go. So it's still a 3-carbon chain. Okay, so that's propan 2-ol. Branching is only possible with 4 carbons or more. Okay, we have question number 30. The infrared spectra of 3 organic compounds are shown. So we have spectrum 1, we have spectrum 2, and we have spectrum 3. What could the 3 compounds be? Okay, now if you look at spectrum 1, I also have the table for reference. Okay, so if you look at spectrum 1 over here, we see a very strong absorption at around 1700. You see it like around 17, I guess this is like 1720-ish, right? Around 1700, right? So that indicates what type of bond being present. It has a C double bond O. Okay, it has a C double bond O. And we can clearly obviously see the CH as well, right? That is this peak over here, right? That's around 2800, 2900, 2950. Okay, that's this range over here. Okay. Now the next one that we have is the next spectrum. If you look at spectrum 2, what does this peak belong to? What type of groups does this peak belong to? A very, very broad OH peak, 2500 to 3000, but it's so broad that you can barely see the CH peak. You can barely see the CH peak. It's a very broad OH peak, a very broad OH peak. This is from a carboxylic acid, right? It's a carboxyl group. And we can obviously see that we can confirm that it's a carboxyl group because we also have this absorption at 1700 due to the carbon oxygen double bond, right? And the last one, we don't have any C double bond O peak. We don't have any C double bond O peak, but we see another peak around 3400 in the range 3200 to 3600. So this must be what? This must be an OH from an, this OH must be from an alcohol. Okay, this OH is from an alcohol. Okay, because first of all, the OH group from the acid has a much broader peak, and secondly, for an acid you'll also have a C double bond O. For a carboxyl group you also have a carbon double bond oxygen, right? But for the alcohol there's no C double bond O, but you clearly see the OH from the alcohol. Okay, so, and this is obviously the CH peak. So that means spectrum 2 is an acid. Spectrum 1 had a C double bond O. Spectrum 2 was a carboxylic acid, and spectrum 3 was an alcohol. So what's our answer over here? Then the answer that we get over here is B, right? Propanone, that's spectrum 1 that had a C double bond O and obviously a CH peak, right? Spectrum 2 was carboxylic acid, that's propanoic acid, and spectrum 3 was an alcohol. It had that OH peak but no C double bond O. So the answer here is B.